Okay, so we know that not all electrons move or are in resonance. If electrons do not move and are not in resonance, they are referred to as being localized. So electrons in sigma bonds are localized. Delocalized electrons are in resonance and are actually more stable than the localized electrons. For a lone pair, in order for a lone pair to be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. Okay, this is important to remember. If you see a lone pair next to a p orbital, so that would be either a carbon with a positive charge or an sp2 hybridized carbon, the lone pair can be delocalized and in resonance. If you see a lone pair that is not next to a p orbital, there is no way for it to be delocalized, and it is what we called localized. Now, this is where it gets tricky. Just because a lone pair is next to a p orbital, so an sp2 hybridized carbon or a carbon with a positive charge, that doesn't mean that it's automatically in resonance. There has to be a couple other things true of it as well. But this is a real quick way for us to identify lone pairs that can't be in resonance. So what does this look like? Well, let's look at our structure. We have a nitrogen next to an sp2 hybridized carbon. So that lone pair will be delocalized and will have resonance. We have both resonance structures drawn out. In one structure, the nitrogen is sp3 hybridized. And in the other, it indicates that the nitrogen is sp2 hybridized. So which one is it? The nitrogen is actually sp2 hybridized. The hybrid looks like a mix of the two structures, okay? The resonance hybrid is a mix of both of those structures, and that forces the nitrogen enough into the sp2 configuration that when we look at the molecular geometry, it actually resembles an sp2 hybridized nitrogen. A lone pair does not participate in resonance if it cannot overlap with an adjacent p orbital. Okay, in those circumstances, it is a localized lone pair. Lone pairs on the nitrogen of pyridine is what we call localized, even though it's next to a p orbital. Remember how I said at the first slide, just because a lone pair is next to a p orbital doesn't mean that it will automatically be in resonance. Okay, so let's look at this a little deeper. In order for a lone pair to be in resonance and be delocalized, two things need to be true. Okay, number one, the lone pair must be on an atom with a steric number of 4. Okay, we looked at this in chapter 1. When it comes time to deciding an atom's steric number, we count sigma bonds and lone pairs. Pi bonds do not count in assessing the steric number. That's the first thing. The second thing, the lone pair must be next to a p orbital, so that's a carbon with a positive charge or a carbon that's sp2 hybridized. These two things must both be true in order for you to have a delocalized lone pair. Okay, so let's look at the structure to my left. Let's start with this nitrogen right here. Is the lone pair localized or delocalized? Okay, well, let's look at its steric number. Now, does it have a steric number of 4? Yes, it does. Okay, again, remember the bonds line structure, we don't have to draw out lone pairs, but we should be able to know that they're there based on formal charge. The nitrogen has no formal charge, and we see 3 bonds drawn out. We know that means it has 1 lone pair. It's got 3 sigma bonds and 1 lone pair, so that means it has a steric number of 4. Great. Is it next to a p orbital as well? Well, in fact, yes, it is. We've got an sp2 hybridized carbon here. We've got an sp2 hybridized carbon here. So it's actually got 2 p orbitals that it's adjacent to. So that lone pair is delocalized. Let's now check out our next nitrogen. Does this nitrogen have a steric number of 4? Well, again, I see 3 bonds and no formal charge, which means I know that it does have a lone pair. But when I go to assess the steric number, I see 2 sigma bonds and 1 lone pair. That gives me a steric number of 3. Can't have a delocalized lone pair unless I have a steric number of 4, so immediately I know it's localized. Okay?